Hello, this is a mathematical solution to the problem of celestial navigation, which is using 3 sextant readings to figure out your position on the Earth. So basically the givens we need to solve this problem are that Earth is a sphere, and that we have 3 sextant readings. For each one we need the time, the date, the viewer elevation, the star name, and the angle it was measured above the horizon. And then we also take as a third given that starlight from any star is parallel by the time it reaches Earth. Then solution is just 4 steps. Basically, first step is finding the GP and the distance to the GP, although this solution doesn't explicitly require the distance to the GP. Second step is get the equation for the circle of equal altitude. Third step is for each pair of circle of equal altitudes, find both intersections. So you got 3 circles, so there's 3 possible pairs, so there's 6 total intersections. Then you do some logic on the intersection points to see which are very close. So the example that we will use just to illustrate for illustrative purposes is MCToon's globe challenge. These are the readings that he gave and the date. So basically, we'll just look at how to get the GP of Arcturus. The time was, in GMT time, it was 5 hours, 22 seconds, 33 minutes. And so the first thing we got to do is get a linear interpolation of the GHA of Aries. So basically, we interpolate between these 2 values here at the 5th hour and the 6th hour, and that gives us, I'll write it down. So for Arcturus, the GHA of Aries at that time, 266 degrees and 15.052 arc minutes. And then we got to get the SHA of Arcturus at that time as well. Here's just a quick diagram to show you the concept. So, like, if you're looking top down on the Earth, here's North Pole, here's the Greenwich Meridian. You basically gotta, to get the longitude, the number of degrees west you are from the Greenwich Meridian, you add the GHA of Aries and you add the SHA of the star together, and that gives you the number of degrees west you are. So the SHA of Arcturus at that time was 145 degrees and 49.7 arc minutes. So we just add these 2 together. So 412 degrees and 4.752 arc minutes. Then we just subtract 360 and we get 52 degrees, 4.752 arc minutes. So then the GP of Arcturus has a latitude and a longitude. Latitude is just equal to the declination, which that's the wrong one. Latitude is the declination, which is 19, see here, declination. It's 19 degrees, 3.9 arc minutes. 19 degrees, 3.9 arc minutes. Longitude is just the negative of that. Minus 52 degrees, 4.752 arc minutes. Okay, so you repeat that for the other 3 stars, get the 3 GPs, and then we'll move on to the math stuff. Let C equal Cartesian coordinates of GPs. And now we have a latitude and longitude, so if we got a sphere here, if we're looking at the surface of the Earth, the way spherical coordinates work is inclination is related to latitude, but inclination is actually measured from the z-axis, whereas latitude is measured from the x-axis. To do the to basically turn latitude into an inclination, we think about, well, what is going to be our inclination? Well, for latitude, we got to go down to the equator, pi over 2 radians, and up by the amount of latitude in the negative direction of inclination. So we let alpha equal latitude in radians of the GP of Arcturus, or whatever star it is, implies phi, the inclination, equals pi over 2 minus alpha. Beta equals the longitude in radians. Then it implies that the azimuth of the GP theta is equal simply to beta. Okay, so now that all implies that c equals, now we just do a coordinate transform, so r, where little r is the radius of Earth, sine phi cos theta, r sine phi sine theta, and an r cos phi. And we want to express that in terms of the latitude and longitude of the GP, so we get r, and now if we sub in pi over 2 minus alpha, that just changes the sine into a cosine. So we get cos alpha cos theta is just equal to beta. R cos alpha sine beta, and r cos changes to sine, so r sine alpha. So there we've got the GP in Cartesian coordinates as a function of latitude and longitude. Okay, so now we want to think about the diagram. So if we have the surface of the Earth, the circle of equal altitude, the set of points where you could be is something like that. Then you have a plane that is intersecting the sphere at that circle. Like here's the GP of the star right here. And then if we look at that side-on, so we're looking at a side-on slice of the Earth there. And here's the point where you are. And here is the GP of the star. So that's point C there. That's you. That's the point we're trying to find. It's very useful to talk about this point P here, which we'll define as just the center of the circle of equal altitude when you're talking about the plane that intersects the Earth. Okay, so if we call this angle here theta 1, then the magnitude of, if we treat P as a vector, magnitude of P is equal to, this is the radius of the Earth here. Magnitude equals r cos theta 1. This here is the distance, this arc length here has that's the distance from the GP. And that we just use a simple formula there. Theta 1 is equal to a over r, so we got cos a over r. That's the magnitude of P right there. And now we let u be a unit vector from the center of the Earth in the direction of the GP. But first of all, let's re-express theta 1. So if we think about this diagram a bit more, you've got the theta 1 here, you've got the curve of the Earth here, and then you've got this angle here is the elevation angle, E in radians. I'm going to call ER as the measured elevation angle, ER in radians of Arcturus or whatever star it is. And this is extended onwards. You think about it, right? Like this line and this line here are parallel. So this angle up here has to be equal to theta 1. And this is a 90-degree angle here, meaning that these are complementary angles. So that magnitude of P there is actually equal to r sine of the elevation angle in radians. What is the vector u? So u is this vector here, right here. U equals 1 over the magnitude of c times the vector c. Like points and vectors are basically the same thing. Like you consider a vector having its tail at the origin. So that equals, so remember what we had c as up here. If we just divide that by r, with all these r's go away, right? Because r is the magnitude of c, because it's on the surface of the Earth. So u equals cos alpha and was it sine alpha? P equals the vector P, or the point P, whatever you want to think about it, equals the magnitude of P times u, because like remember p is in the direction of the unit vector. Like the unit vector u points towards p. Our sine of the elevation angle, and u is just equal to that there. So, alright, so now we've got the point P. If we go back up to this this diagram here, this point here P is in the plane, and we have the unit vector u there. So that defines a plane, and if you remember from linear algebra, if we have a plane and you have a point P in the plane, and you have an arbitrary point X in the plane, the equation for the plane is X minus P vector, point vector, same thing, times the unit vector normal to the plane is equal to 0. So that implies X, Y, Z, our arbitrary point, minus px minus py minus pz dot u is equal to 0. That implies that u dot product is commutative. Equals u dot p. And u dot p, well, that's simply equal to magnitude of p dot u. We're just using this up here for p, and then dot u again. Unit vector dot itself is just 1, so it's equal to the magnitude of p. We had the expression for the unit vector right here, so we just dot that with x, y, z. So that implies that x cos alpha cos beta plus y cos alpha sine beta plus e sine alpha, magnitude of p was our sine of the elevation angle, our sine of elevation angle in radians, and that's the equation of the plane. Once we have the equation of the plane, we need two perpendicular unit vectors in it to define the equation of the circle of equal altitude. We want to define this, this circle that goes around here. We're going to do that with just some arbitrary unit vectors that are orthogonal to each other. That'll allow us to define the equation of the circle. So we're just going to pick an arbitrary point on that plane. Just set x equal to 0, y equals 0. That implies z naught equals r sine of the elevation angle in radians all over sine of alpha. So that implies 0, 0, z naught is belongs to the plane. It's a point on the plane. And if sine alpha was equal to 0, that would cause a problem, but there's no star that has like a GP on the equator, so you won't run into that problem. Now, when we think about our plane here, we've got our point P, which is the center of the circle of equal altitude, and then we got this point here, 0, 0, z naught, and that is a point in the plane, so this vector here, 0, 0, z naught, minus px, py, pz. That's a vector in the plane. Meaning if you, so if you have the tail of the vector at p, then that vector stays in the plane. So now we define v1 equals, we'll call this h, 1 over the magnitude of h times h is a unit vector in the plane. Any vector that's perpendicular to u is in the plane. We want like a vector that's perpendicular to both of these vectors. So the obvious thing here is to take the cross product. v2 equals v1 cross u is perpendicular in the plane. Okay, so now given these two unit vectors, we find the equation of the circle of equal altitude. That is simply going to be f of t, and t is just basically an arbitrary angle, equals point P plus rp, I'll define that in a second, cosine of t v1 plus rp sine of t v2, where rp equals radius of the circle of equal altitude in the plane. So I'll just show you, like, this distance here, from here to here, that's rp. This distance here is rp. Alright, so we have p, we have rp. How do we find rp? I should say how you get rp there. rp is just this distance here. rp is equal to r sine theta 1 equals r cos elevation angle in radians. Alright, so we have the elevation angle given, we have the radius of Earth given, so we know rp. So we know rp, we know v1 and v2, and we know p, so we have the equation of the circle of equal altitude. And then we do a similar thing, g of w, that's the equation. We do the whole process again for another star, like star 2, like for example in MCToon's challenge here. He has star 2 Polaris, so we would repeat the whole process for Polaris and get another function for the circle of equal altitude in Cartesian coordinates. So q plus rq cos w u1, nothing to do with the u from before, so this is like the v1, plus rq sine t v2. So that is the equation, is the equation of the circle of equal altitude of star 2. Okay, so now we get a nice system of equations that we can set up there. We set f of t equal to g of w, solve for w and t. I'll just jump to it. So px plus rp cos t v1x plus rp sine t v2x. I need to move that over a little bit to give myself some space. Equals qx plus rq cos w u1x plus rq sine w u2x. Py plus, we're just basically doing that for the y components now, rp cos t v, it's all y coordinates, u1y plus rp sine t v2y equals qy plus r q cos w u1y plus r q sine w u2y. And then finally we have, for the y component, for the z components, rp cosine of t v1z plus rp sine t times v2z equals qz plus rq cosine w u1z plus rq sine w u2z. And that's a system of equations that can be solved. You can set it up. I'll just write out what the system of equations will be. Actually, first I'll just just to make our life a bit easier, we'll define x equals cosine of t. Sorry, x1 equals cos of t. x2 equals sine of t. x3 equals cosine of w. And x4 equals sine of w. And then, so x1, 2, 3, and 4 are the variables that we're trying to solve for with these three equations. Doesn't seem like enough, but it will work. So basically, we got the system rp v1x x1 plus rp v2x x2 minus rq u1x x3 minus rq u2x x4 equals qx minus px. Alright, and that will be our system of equations that we're trying to solve. You do Gaussian elimination on that, and that will give you something that looks like this matrix here. So you will have a matrix, will be a 1, a 0, a 0, some number, and some number. You'll have a 0, a 1, a 0, some number, and some number, and you'll have a 0, 0, 1, some number, and some number. This is the line that goes through there. So these are the coefficients of our x variables, and this is our constants. So we're going to define negative b1 to be this number right here. And we're going to define b2 to be this number right here. So if we read off what the bottom row, or the third row of the matrix from the Gaussian elimination looks like, we get the equation cosine of w minus b1 sine of w equals b2. That implies that cosine w equals, that's why I made a minus there, so that we get a plus here, sine w plus b2. And we square that to get cosine w squared equals so b1 squared sine w squared plus 2b1 sine w plus b2 squared, and that is equal to, if we look at this here, cos squared is equal to 1 minus sine squared, 1 minus sine w squared. And then that's a quadratic in sine of w. So we rearrange the equation, and then we get how much sine of w do we have. So we got b1 squared plus 1 sine of w. How much sine of w do we have? 2b1 sine w. And how much constant do we have? b2 squared minus 1. I forgot just got to do a quick fix there. I forgot to write in the b2 when I was squaring the equation. So then 2b1 b2. So now we solve that. That implies sine sine w equals negative 2b1 b2 plus or minus square root of 2b1 b2 squares minus 4 b1 squared plus 1 b2 squared minus 1 all over 2b1 squared plus 1. These b values were given because they came from the Gaussian elimination. Let 3 and b3 prime be the two roots of the quadratic equation. So we have three cases because we want to solve for w. So if b3 equals 0, then we look at this graph of here's w. Here's sine of w, and so we're plotting sine of w against w. And if b3 is 0, then the possible values for w are these two here, because we're just going to arbitrarily decide that we want w to belong in the range 0 to pi. And so that implies w equals 0 or pi. If you know about the pi function, these two values here are 0 and pi. So then that's if that's the case for b3 equals 0. If b3 is greater than 0, then let's look at that case. So basically we have we'll plot here's w and here's sine of w. Now if b3 is some constant value as a function of w, we want to find when sine of w equals b3, basically. These are the two values. So we know that this little distance here is equal to the arcsine of b3. And then we know that, again, this distance here is also equal to the arcsine of b3. So that implies that our two values for w are going to be arcsine of b3 or w for w equals pi minus arcsine of b3. So that's that case. And then our last case is when b3 is negative. So if b3 is less than 0, then we're going to plot our graph here. So there's the w-axis. So if b3 is somewhere negative here, And these are the 2 points we want. So what? So basically, if we think about the arcsine function, it actually just goes from here all the way down to here. So this value here would actually be the arcsine of B3. So think of it, it's this negative value here on the number line. But we want to add 2 pi to that, basically to get us over here. So one possible answer is W equals arcsine of B3 plus 2 pi. And then we think about the other. We think about how do we get here? Well, if we just look at this point here, this point we know from the sine of x graph, this point is negative pi. And then we want to subtracting a negative value brings you to the positive direction. So the other possible answer is W equals negative pi minus the arcsine of B3 plus 2 pi. So those are our possible answers there for W. So you notice in each case we got 2 possible answers for W. Those are going to be our 2 intersection points. So if we go back up to the, actually I'll draw it again here. So if we think what we're doing here, we got the surface of the Earth. We got one circle on the Earth. Then we've got another circle on the Earth, and with the GP there, and then we have these 2 intersection points. And if you remember what we did, we defined a plane. Basically, if we think the point below, we had the 2 orthogonal unit vectors. We don't know which way they are pointing, but we know. But basically, we know we have the equations of the circles of equal altitude, and we know that when basically, if we go back to our equation G of W1, that's the first possibility for W, equals the first intersection point, and G of W2, right? Like this would be W1 and this would be W2 or whatever, doesn't matter. That equals the second. And then when we do that so we've completed this process now, and then we do it for all 3 possible pairs, we get 6 intersection points. And then, so basically we had the 3rd circle of equal altitude. And we'll have these intersection points here. And these 2 intersection points here. And we see we have these 3 intersection points here clustered close together. So you basically just do some logic on that and basically take the average of these 3 points, and that is your location fix. So that's basically the way you approach this problem. I think it's a pretty simple solution. And so I made a spreadsheet that will do all this for you. So for example here, I've plugged in the values for MCToon's globe challenge for the sextant that he put out like almost a year ago. Basically, I entered in all the data here. Here's the time of the observation for Arcturus, all the other things, the measured elevation angle, R is GP on the hour before the observation, on the hour after observation, the SHA of Arcturus, declination of Arcturus. And then I did the same thing you input for the second star, which was Polaris, and you input it all for the third star, which is Procyon. And then all this, the spreadsheet basically does the Gaussian elimination with, the spreadsheet basically calculates the unit vectors, calculates P, like it calculates all that stuff, does the Gaussian elimination to solve for W, gets the two values for W, and then finds the two intersection points by plugging in these points into the circle for the an equation for the circle of equal altitude. So then basically intersection point is the latitude and the longitude. And yeah, so then when you get down here, you just we have the all 6 intersection points. Then we just do some logic on that, and because you can kind of tell, right, like which ones are all close together. Like we look at this from the first intersection pair, like this is from circle of equal altitude 1 and circle of equal altitude 2, or star 1 and star 2. Here's your 2 intersection points, and you look at, then here's your second set of intersection points, and you notice, well, this one is really close to this point. And then you look at the third one, well, this point is really close to these 2 points. So then these 3 are the correct intersection points, and you just take the average of those. Yeah, it's an inaccurate fix, but yeah, you just get the location fix. So I just take the average of the 3 intersection points, and this is the final answer here. So the final latitude is 46.8298 degrees, and the longitude is negative 93.406 degrees. And so yeah, so I'll put a link to this calculator here so that you can use it yourself. It's pretty. All you gotta do is just plug in the sextant readings, and that's basically done for you. So I hope you find that useful.